So in this chapter, what we're looking at is we are going to be studying the speed of chemical reactions, and that is called kinetics. We'll be studying the factors that affect rate. You've studied them in AS level and O levels also, the factors including temperature, pressure, concentration, surface area, and catalyst. We've also seen the effect on molecular energies with regards to temperature and also with regards to activation energy and catalysts. Now, to study what we're going to study in AS and in A2, sorry, in more detail is how concentrations affect rate. But before we do that, what we also have to do is how do we define rate? So how do we define the rate of a chemical reaction? Basically, right? So that's the first thing. So how do we define rate? So what is rate? It basically is the how quickly the concentration of a product is increasing or how quickly the concentration of a reactant is decreasing. So it's basically the change in concentration. So it's the change in concentration of either the reactant or product with respect to time. And because of that, its unit as a numerical value is the rate of change of concentration, which is moles per dm cube per second. The SI unit for time is second. So the SI unit for rate is moles per dm cube per second. I'm sorry, not the SI unit, the unit we use in chemistry, because SI unit for volume is meter cube. This is dm cube. So the unit for rate for us is moles per dm cube per second. At times, in the real world, we also have moles per dm cube per minute if you're measuring the time in minutes and not seconds. But most cases in the exam, the units used for time will be seconds, and the unit for rate, therefore, which will be change in concentration per time, is moles per dm cube per second. And this is how we can define average rate. The rate that you would say that, okay, in about 30 seconds, 60 cm cube of gas is produced. So using that, you'll find the moles and volumes moles per dm cube. And we can use it for gases and solutions, and mainly for gases and solutions. But what we're going to first study is just as the trend in the change in concentration for reactant and for product. So when you have a reaction, which for example is something like this, where you have reactant R making a product P, the idea is that as time increases, the reactants decrease and the products increase. So how does that look like? So what happens is over time the concentration of the reactant starts to decrease and the concentration of the product starts to increase. And there's this little graph that I've also given in the notes. Will come in handy to understand what's happening. So as the time progresses, this is the reactant's concentration. So it starts with maximum, and over time the concentration of the reactant decreases till it becomes 0. While the product initially was nothing, then you made product, and over time the product increases. One thing you'll note also is that eventually all the reactant will become 0 and all the product will have formed, and after which there'll be no more product forming. And secondly, if you notice the steps, the increase in the concentration of the product is also not constant. It's greater initially and it's less towards the end. Similarly, initially the rate of the change in the concentration of the reactant is high. Big drop, then smaller, even smaller. And you've probably seen this graphically also, that this is decreasing greater initially and slows down. You've seen product graphs in O-level ATP. Let me show them to you and you might recognize them. So here, if I plot the concentration of reactants and products against time, what you will realize is that the reactant decreases with time, product increases with time. And here you'll notice that the gradient, it seems like there's a larger drop initially and the drop decreases, and there's a larger increase initially and the increase decreases. What you need to realize is that the gradient here is the rate of change of concentration. So the gradient here is the rate of the reaction, magnitude wise, because initially there's a high rate and over time it decreases and it becomes 0. And these are the change in concentration of reactant, change in concentration of product. You can study either or. they will still show you the same exact thing, that the magnitude of the gradient, if I draw tangents here, decreases, and if I draw tangents here, that also decreases. Let's show an actual experiment right now. If I show an actual experiment with what you call it, let's say sodium carbonate and acid reacting and collection of gas, what you'll realize is that truly, as the reaction proceeds, less and less of that gas is collected. Let me show you a graph. So if you can imagine that this is what's happening here in this particular setup. You got carbonate and acid in here, and when you collect this setup, you got carbon dioxide being released here. Now over time, the gas collected increases, but the rate at which the gas being collected is decreasing with time. Eventually it becomes zero. And the reason for that is that initially you got the largest concentration, so the largest rate of reaction is initial. The fastest rate of reaction is at the start. And that's the maximum gradient. Over time, if I make tangents to the graph, which is this purple line, this is the first tangent, this is called initial rate. This is rate at a certain time, which let's say time equals to 40. And what we are actually finding is, we are finding three different types of rates. We're finding what we call initial rate or instantaneous rate at any given point. So when time equals to 0, you found a rate, that's the rate time equals to 0. This is rate at time equals to 40. This is probably rate at time equals to 90. And at this stage, the rate has become 0, which means the reaction has stopped. You've definitely seen this graph in O-level ATPs or IGCSE ATPs. And what we're going to study is basically the idea that when you draw a graph like this, you can study the rate by measuring the gradients at any point in time. Literally drawing tangents by lines and then finding their value. So that's how we calculate rate at any given point. Now, if I had to look at this more closely, the gradients, this would be an easier understanding, that if you have a product, you'll notice that the product starts to increase, and over time, the rate at which it increases slows down. And so here are 4 sections of the graph. At each section, the gradient on the tangent is drawn. And you notice these are the 4 tangents. At the initial time, that's the largest change in a small amount of time. That's when the reaction is the fastest. Over time, the change decreases. So the gradient, if you notice, becomes less steeper, and at the end, there is no more product formed, and the gradient is now 0. Largest gradient, slower, and 0. And so initially the rate is the fastest, then slower, and eventually becomes 0. Understand that the rate is here the gradient. The gradient of what? The product time graph or the reactant time graph. All right. And the 3 terms that I want to talk about is average rate, which generally is what? Is the total change in concentration over total time taken. Instantaneous rate is rate at each of these 4 instants. 1, 2, 3, 4. And the most important instantaneous rate for us generally is the initial rate. Initial rate is the instantaneous rate at time equals to 0. So that means you draw a tangent at time equals to 0 and you find the value for that tangent. So rate at any given point in a concentration time graph is instantaneous rate. It keeps changing. Final rate will eventually be 0, but initial rate is the maximum or the fastest rate. All right. And this is just a summary of basically following rate through graphs. We look at graphs in more detail later. This is just the introduction of what represents the value for rate. So rate is not constant. It changes as the reaction changes. Initially greatest, over time slower. All right.